They should be kept carefully separated. All right. Here you go. So this
goes behind my head, I think.
Yep, just like that over here. And then this flips. Looks like it's on.
Test. Yeah, is it working?
I think it looks like.
Okay.
Yeah, just click that somewhere. Stick it in your pocket.
Yes. Is it working? Yes. Test.
I think it's fine. Yeah.
Thanks.
So I think we can start the session. That looks very complete. So in our session now we have 3 talks. Unfortunately, the last talk not take place. This means we have more time with the 2 presentations. Then I think we can get maybe 5 more minutes.
That sounds good.
So then presentation is from Mario Petrinka. So he will be showing how one can use machine learning to maybe model the collision process and what are the advantages and challenges in this respect. The floor is yours.
Thanks for this kind introduction. I'm grateful to start this section here at this conference on neural networks, which I would like to start with the following question. What is the potential of machine learning within the lattice-Boltzmann method? So based on the literature available and the publishing dates of currently relevant papers, we are just at the beginning stages to answer this question completely. However, I try to adapt to give one possible answer to this question by introducing you to a neural network enhanced collision operator under robust constraints and equivariant constraints. So over the past decade, interest in machine learning has rapidly increasing, or the interest had rapidly increasing. And in this context, a lot of libraries has been developed. And thus that motivated us to develop a lattice-Boltzmann framework built on one of these libraries, for example, PyTorch. And that enables us not to incorporate machine learning algorithms into the lattice-Boltzmann method, but also to accelerate the numerical operations to be run in parallel on the GPU. So a few years ago, I presented a neural collision operator in 2D with promising results. And today, we are going to extend this neural collision operator to 3D when I'm talking about the training procedures and about our thoughts we had in this procedure. And last but not least, about the results and the transferability properties of this neural collision operator to 2 different flow applications, despite it is trained on a completely different field. So in its fundamental form, the neural collision operator is an adaptive multi-relaxation time model. We have our transformation matrix M based on Hermite polynomials to map our distribution function to moment space, where we relax our moments towards the equilibrium by relaxation rates. So we set the relaxation rates for the conserved moments, density and the velocity to 1 for the D3 Q27 stencil. And as in the KBC model, the relaxation rates for the shear rates is connected to the kinematic viscosity and is, as you know, determined by this formula as in the BGK operator. So the question now is how to determine the relaxation rates for the higher order moments. And our idea was to group the moments respectively to their order, group these moments and determine the relaxation rates for these orders. So for this, in this example, we have to design a neural network to determine 4 relaxation rates at each time step and at each local node. How to do this? So we have our moment basis at each local node, and based on Hermite polynomials, we have 27 moments grouped into 7th order, and we are using all of these moments as input features and applying these to a shallow network based on 20 neural nodes. And these hidden network is then calculating for temporary relaxation rates. So we have 644 parameters to be optimized. So temporary relaxation rates, because when we are going to apply these to an exponential function to guarantee that the output becomes definitely larger than 0.5 to enhance and accelerate robustness in our neural collision operator. So this was the prototype a few years ago. Then we have one challenge remaining. So as an example, here's a two-dimensional doubly periodic shear layer on the top left corner. And when we are now using Hermite polynomials to achieve our momentum basis, we have an exact rearrangement of our moments. When we now achieve or apply these moments to our neural network, we achieve a simulation output or relaxation rates that will not be the same when we rotate our initial flow field by 90 degrees, because when the inputs for our neural network will rearrange. And this arrangement is essential for the output of our neural network. So the underlying physics is the same. The outcome of our results will be different. So we looked at other sectors of science that has to handle the same issue. So imagine that we have a picture and we want to apply image recognition. We want to detect the cat, the cow, or the dog, independent from its initial orientation, if a picture is rotated by 90 degrees, reflected, and so on. So in this case, or in this step, equivariant networks comes into play. We are using the dihedral group D4 that determines all symmetries available for our stencil. For the D2Q9 stencil, we have 8 different symmetries achieved by rotation operations and reflection operations across the axis, and the rotation multiples by 4. For the D3Q27, we have 48 different symmetries, and we are using all the symmetries to apply to our neural network to achieve our relaxation rates. So the computational demand is quite large. So now we have here in this example 3 rows, but finally 48 different momentum bases at each node for each different symmetry. And now we are applying each symmetry to our neural network in between a ReLU activation function. And each momentum basis determines the temporary relaxation rates. And after all the 48 momentum bases are applied to our neural network, we do an average over all these 28 relaxation rates and achieve again the temporary relaxation rates that we apply to the exponential function to achieve that the output becomes larger than 0.5. So now we have a neural network that determines the relaxation rates independently from the starting orientation. So now let's come to our thoughts on the training procedure. Our motivation was to train our neural network on turbulence behavior. So this led us to the forced homogeneous isotropic turbulence flow. And the huge advantage is that we can achieve an infinite pool of training data and starting velocity fields. So we have a 0 initial velocity field and introducing energy by a spectral force introduced by Alvenius et al. And this enables us to introduce energy into the larger scales formed by a Gaussian function in Fourier space. And by a random generator, we can stimulate randomly amplitudes and phases. And by an inverse Fourier transformation, we achieve our randomly accelerated force fields. Here in this example in 2D, and this can also be mapped to 3D. So at this point, we can achieve an infinite pool of training data. In this example, we have 40 different initial flow fields as ground truth on a resolution of 256 to the power of 3 as DNS data. And we are mapping these to a Corsa grid by acoustic scaling to achieve the training batches that are then applied to our neural network as an initial field on a grid size of 32 to the power of 3. Then we are going to start the simulation using this neural network and applying after a defined simulation step our loss function, which describes the mean square error of our energy spectrum of a forced isotropic turbulence field of the energy spectrum in the wave number range from 4 to 10. Why not the first 3 wave modes? Because they are fluctuating due to the method used to accelerate the flow. So we have a Gaussian function, and the first 3 modes are accelerated. So we have a fluctuation of the first 3 modes. So we are minimizing the discrepancy in the wave number range from 4 to 10. Last but not least, the last wave number is also taken into account to adjust the dissipation behavior of our neural network by a weight omega. And adjusting this weight, we can either achieve excessive over dissipation by setting this weight too high. So we have this energy spectrum here. And when we are setting this weight too low, to 1, we minimize the discrepancy in the wave number range from 4 to 10. However, energy is accumulated in the higher wave number range, which is not desirable. So by experimenting with this weight, we can achieve a model with a good agreement between these two by, in this case, setting this weight to 20. And to increase robustness during the training procedure, the steps after the loss function is applied is increased after every epoch. So at the end, we achieve to simulate 1 time scale to apply the loss function. Why not longer? Because we are simulating or training our neural network on a GPU A100 with 80 gigs of RAM, and the RAM is completely full on a lower resource simulation because the training procedure is quite memory demanding. So now let's talk about the results. Our first evaluation process or benchmark is the Taylor-Green vortex in 3D. On the left side, we have we are using a resolution of 32 to the power of 3 for different Reynolds numbers and comparing different collision operators, the VGK operator, the KBC operator, and as a ground truth, the reference simulation calculated on a grid size on 512 to the power of 3. And on the left side, the same for different Reynolds numbers on a grid size, on a resolution on 128 to the power of 3. So what can be seen is that on the left side, the BGK operator crashes when turbulent intensity increases, probably about 5 seconds. And as expected, the KBC operator stays stable, as well as the neural collision operator, here in short, NCO. And on the right side, you can see that the neural collision operator is in a good agreement with the reference simulation. And in this case, it performs better than the BGK operator as well. So last but not least, we simulated the second benchmark case, a cylinder flow in 3D on a Reynolds number of 3,900. With this configuration, we have lateral periodic boundary conditions, equilibrium inlet and outlet conditions, and between the solid and the fluid, we have interpolated boundary conditions. So on the right side, you see the velocity profiles at specific points behind the cylinder, averaged in time over the height of this domain. And even here, we can see that we are in a good agreement with the reference, for the velocity in flow direction, velocity ux, and uy. So the flow is also suited to simulate obstacle flows with proven transferability at this point. So what should be left? One main issue at the moment is that the efficiency of this operator is not as good as expected or as hoped, because we have this huge amount of data applied to our neural network, and this makes this completely new collision operator very slow. So I have some issues at the moment, or ideas to handle this issue at the moment, but these need to evaluate it as well in the next few weeks. So let's come back to my first question. What is the potential of machine learning within the lattice-Boltzmann method? It is definitely suited to tune parameters effectively at the moment. And yeah, now I'm looking forward to hear what the other answer is for the next presentation. And I'm looking forward to your questions. Thanks. Oh, that's good.
So I disagree. First thing, I disagree with your number of relaxation rates. So this was either 4 or 5 that you had.
4.
4.
Yes.
4, right. And so you spent a lot with the symmetry of your data, but you were not spending time with the symmetry of your relaxation rates. So the third order moments, they can be split in 3 different. Yeah, the fourth order can be split in also 3 different. So this makes 6. Then you will have 1 for the 5th, and also this would make 7 or 8. Yeah, I believe altogether we have 10. If you take everything, including the ones that are hydrodynamic, we'll have 10.
Yes, but can I say something?
Yeah.
Yeah. Thanks. Within one group, the symmetry the moments have is incorporated within the group, isn't it so? So,
no, inside the group. For example, you will have a moment. If you count them up, they will be a moment 2, 2, 1, 0, for example, right? So
order moments. Yes.
So like there's something that is second order in X direction, first order in Y direction, 0 order in Z direction. Yeah, and then you have one that is second order in Z direction, first order in Y direction, and 0 order in X direction. And of these 2, you can form the sum and the difference, and they behave differently. Sorry. We have time. Okay, there's an important. I believe there's an important discussion. I believe so. So you would have more moments, more different relaxation rates than
you can choose so,
yes.
but well, in the KBC model, you have 1 relaxation rates for all non-hydrodynamic moments, and I'm using 4. Splitting these on the moments they have that have symmetry properties.
Yeah, so I mean, there's of course a reason why I said this. I'm sorry for making advertisement for my own work, but something 2017, I derived an analytical solution for the optimal relaxation rates. Yeah, and there it is very important to set different relaxation rates for the sum of the third order moments and for the difference between.
Okay.
It's very important to have the difference, and I also have a comparison of this Taylor-Green vortex where we do it with the entropy, which is looks a little bit different. Yeah, but I think this would be the fair comparison here, because you do machine learning optimization. And there is already a solution that, at least I claim, is the analytical solution for the rate. Right. So this would be the interesting comparison here.
You said entropy, so the energy dissipation is based on the entropy.
Yeah. So this looks a little bit different because, I mean, if you plot, we also plot the energy dissipation. If you plot them, they look a little bit different.
I didn't get it. So in this case, the energy dissipation is calculated by the kinematic energy, incompressible energy, and you calculated by the entropy.
Yeah, we did.
And the kinematic. Okay.
Show it. I mean, we show it from the extrusion.
Okay.
So there is also discussion.
Yeah.
Yeah, thank you.
As the last time.
Yeah.
It's interesting work, but so if I understand this right, the only thing you're optimizing at this point is the relaxation rate,
Yes.
not the moments themselves,
No.
not the equilibrium distribution, which in principle will give you a lot more degrees of freedom that you could look at, right? So if you think back to Ilya's talk this morning, so you could sort of, I presume you use this quadratic equilibrium distribution, you could use an entropic one,
Yes.
and do a similar procedure there. You could see whether or not those, behave more reasonably. So have you looked at?
No, not yet. But it was an upcoming idea when I heard about this presentation this morning. Yeah.
Thought about looking at time dependencies of relaxation parameters. So they're not just looking at a single snapshot in time, but taking into account maybe a little bit of history. I'm thinking of things like collision operators for viscoelastic fluids.
During the training procedure or no? Not at the moment.
So you have a slide about these different symmetries that you have to deal with. And if I understand it correctly, the way you deal with having multiple symmetries is that you basically rotate your data, say 8 times in 2D, run it through the
Yes.
that 8 times
Yes.
and then average.
Yes.
Could you instead have some sort of pre-processing and post-processing function that basically, so that you don't have to run the neural network 8 times? So train on just 1/8 of your.
So a few years ago, the idea was that the neural network should learn exactly these properties.
Okay.
But in image processing, or there was an recently published paper regarding the lattice Boltzmann method, also incorporating equivariant networks, that showed that it was quite faster when you introduce physical constraints directly to the architecture. Otherwise, you want the neural network to learn this behavior, but you can set these constraints in the architecture directly.
I have a question from my side. So,
Yes.
what do you consider good accuracy training?
Excuse me. Okay.
What is your accuracy of the training? So when do you consider that your network is trained?
Yeah, that was a hard process. I didn't make any evaluation plots because I increased the time steps after every epoch, and this led to a loss function that was fluctuating, also doing new force fields that were applied to. So I have no metric to identify this exactly. But yeah. Thanks.
Good. Yes. Okay. Can I use this? Oh, this is yeah. And good afternoon, everyone. It is a great honor for me to mic up so that the microphone call.
So next presentation is from Cao Li.
Yes.
So then it's a very interesting topic.
Yes.
This is
Oui.
Yeah.
Oui.
It's very interesting to see how the technical model will adapt these behaviors. So please go ahead.
Okay, good afternoon, everyone. It is a great honor for me to stand here and share our research work with all of you. And today I will present our research titled Numerical Simulation Research on Fish Refuge Behavior based on Deep Reinforcement Learning and Immersed Boundary Lattice Boltzmann Method. And firstly, I would clarify that it's a application research. So, and yeah. Oh, sorry. And my talk will be divided into the following parts. Firstly, I will briefly outline the background and the motivation of our research. Fish have evolved to become excellent swimmers with great hydrodynamic efficiency over millions of years, and they have evolved many different swimming behaviors. They can utilize vortices while swimming to minimize energy consumption, and also have high maneuverability in both initiation and turning performance. Well, starfish swimming behavior has a lot of scientific and engineering significance. In biomechanics, we could understand how fish utilize their body shapes and muscle structures to move efficiently in water. And in evolutionary biology, we could understand how different species have adapted to their ecological niches and how these adaptations have influenced their evolutionary paths. And in biomimetics, the swimming motion and body structures of fish provide significant insights for biomimetic designs. Well, in the field of engineering, high performance AUV and high efficiency underwater robot swarm formation could be designed, and there are also some intelligent fishery design and environmental applications. Okay. So physical experiments possess a large volume of experimental data to reveal the kinematics and dynamics mechanism of fish locomotion, but it has some limitations, such as high experimental costs, challenges in controlling live fish, and limited information obtained through non-intrusive measurement technique. And then numerical simulation is another powerful tool to study fish swimming behavior. And through safety methods, the fluid mechanics of fish locomotion can be accurately analyzed, and this providing more precise quantitative results. But for numerical simulation, complex fluid model need to be established and numerically computed, and this requiring significant amount of time and computational resources. More importantly, the simulation of fish behavior and movement is predefined through computer programming. With the coming computer science and technology advancement presents a chance for researchers, so many interdisciplinary studies have emerged. It provides an additional decision-making module for digital fish, and through artificial intelligence, and also allow digital fish to learn optimal behavior strategies through interactions with the digital environment. But rely on global information inputs, and the digital intelligent fish like the active perceivability has become the limitation of this method. Okay, so the challenge is how to achieve real-time feedback and response by intelligent fish to continuous and steady flow fields. And how can we use intelligent fish as autonomous and independent explorers in digital environment to reduce the impact of global artificial information on their decision-making process? To address the above challenges, we proposed a novel fish simulation platform based on deep reinforcement learning and immersed boundary lattice Boltzmann method. Firstly, input of environmental information from the perspective of individual local explorers of fish. And secondly, a lateral line machine based on CNN integrated to platform, and this enabling digital fish active perception, feedback, and response to noisy flow field environmental information. And it also shows some efficient training strategy transfer and robust generalization. Okay, and our computational platform is divided into the following parts. Fish body and a flow field boundary conditions pre-processing module is responsible for mapping real-world boundary conditions into digital space. Yeah, and then transferring them to digital hydrodynamic field and a fish body kinematics module. Fish biological characteristics module provides a universal interface to enable the simulation of diverse fish biological functions. And the multi-modal intelligent fish perception and the decision simulation module is interacting with the digital hydrodynamic field and fish body kinematics module, and perceiving and processing information, making decisions, and controlling the physical motion into the digital space. And utilizing the aforementioned paradigm, it is expected to achieve an end-to-end simulation of complex perception and decision-making process of intelligent fish in multimodal digital environment. Okay, the decision model is a core component of the entire research. So we designed this module using deep reinforcement learning algorithms. Specifically, we use the soft actor critic algorithms. It has some features such as off-policy learning, entropy regularization, actor critic architecture, and stochastic policy. Well, deep reinforcement learning is analogous to embodied intelligence tuple, such as perception, exploration, feedback, and decision-making, and so it is well suited for our tasks. Well, for digital free solver, we use the immersed boundary lattice Boltzmann method to achieve the fish body and flow field interaction. It has many advantages, and the reason why we use this method is, firstly, it is easy and low cost of generating new data for deep reinforcement learning training. And secondly, it is easy to deploy large-scale GPU parallel computing, and also we are suited for large deformation FSI simulating. Where flow vision and physical vision are critical components of the multimodal perception of fish in the environment, and the flow vision can provide flow patterns and vortex structures of fish. It is crucial for them to swim in the aquatic environment. So in reality, live fish often use their lateral line organs to achieve the flow vision. And here in cyberspace, we use DNA structure-based lateral line machines such as CNN, RSTM, and Transformer, et al. And in this case, we use CNN to achieve the intelligent fish's flow vision. And the physical vision enables fish to rapidly identify objects, and it is commonly used for navigation, target recognition, and obstacle avoidance. So in reality, live fish often use its ocular organs to see something in water environment, and robotic fish often use cameras and other vision-based sensors to see obstacles. Here in cyberspace, the absence of light source prevents a physical reflection of the obstacles. So we use one-hot binary encoding to achieve the intelligent fish's flow vision. And here are some simple cases using a computational platform, such as fish's predation swim, reotaxis, and fish's common gate in water street. And this case demonstrates how the intelligent fish use a lateral line machine to achieve the perceive feedback memory process of the complex fluid environment. And the simulation results exhibit good consistency with the experimental data. Next, I will present our experimental design and results analysis. So in this case, a 2D hydrodynamic field design to simulate the predation and refuge behaviors of fish, and in a coral reef was established. The kinematics and the dynamics of environment food are simulated using the Eulerian Lagrange method. And in the flow field, we could see that the obstacle was represented by a 2D cross-section of 3D coral reef model. And the environment food was from upstream to downstream, and there are one high velocity mainstream, and there are two habitats for intelligent fish to choose. And the hydropeak comes, they can come into the refuge habitats to avoid the hydropeaks. Well, for deep reinforcement learning setting and long heuristic rewards designed for the interaction between intelligent fish and the digital environments. Long heuristic rewards does not encourage agent do or not do something. So they're primitive and fundamental, and this enabling algorithms to learn solely from the laterally obtained environmental feedback. And for reward setting, the energy cost, the number of food get from the environment, the velocity perceived by the lateral line machine, and the fish's hunger time, and the fish's energy remain were both considered into the reward setting. And for the state setting, and one historical state was integrated to the current state, and to enable the agent, to enable the intelligent fish has the ability to recognize the memory and historical state and one recent state. So for boundary conditions, and the inlet boundary conditions are classified as high environmental pressure and low environmental pressure. And the high environmental pressure boundary conditions is characterized by denser and longer duration hydropeaks. And the experiment was conducted over 100 episodes to ensure the statistical significance of the results. Okay, in low pressure environment, we could clearly say that the strong fish exhibit and involved more aggressive predation strategies, and the weak fish are compared less and the strong fish showed the less refuge times and more survival times in this environment. And in high pressure environment, the strategies involved by strong fish and the weak fish are more distinguished. Well, even in such conditions, we could say that the strong swimming ability and we call this involved bold personality, and enables the strong fish to acquire more food rewards from the environment, and the weak fish are compelled to adopt more frequent refuge behavior, because if they don't, and they won't survive as long in this high pressure environment and high flow environment. Yeah. And this really affects their long-term living ability in this high flow environment. Okay. And finally, I will summarize our main findings and contributions of our research. So we designed an end-to-end trainable intelligent fish simulation platform based on deep learning, reinforcement learning, and immersed boundary lattice Boltzmann method. And it is used to study various scientific and engineering questions related to fish. And in the fish refuge behavior simulation case, and through long heuristic reward design and end-to-end learning, and the strong fish in the same environmental reward setting to the weak fish, and they are involved a bolder personality, and the adaptations allows it to secure more food rewards and exhibit shorter refuge times. And although weak fish are, we could say that they have involved a shy personality, and they take refuge more frequently and obtain less food, and such refuge behaviors is a necessary condition for them to occupy habitats in high flow environments, and otherwise only strong fish would occupy the ecological niches in these high flow environments. And the application of this platform is anticipated to play a crucial role in various domains, including digital twin in hydraulic engineering and ecological environmental engineering, and some biomimetic research and EDO. Okay, thanks for your listening. That is all my presentation.
Very much. So please, questions, go ahead.
How do you define strong and weak fish?
Sorry?
How do you define a strong fish and a weak fish?
Strong fish. Oh, it's a tail frequency, and the strong fish has a high tail frequency. We have used NACA 0020 and to achieve the fish body. Yeah, the same body, and but we attribute the different tail frequency for them to, yes, strong fish and yeah, and it is actually chosen by the fish. The action. Excuse me. Frequency what?
So what is the learned from the fish? So what does the fish learn? So you have a map, a column with different rewards. Could you go to the slide? So maybe you go to the slide before that you had this reward.
The loss function. Yeah. What's the loss function?
Oh, loss function. And the loss function does not show by here because and we will loss function in the reinforcement learning is 这个怎么说？不好意思 sorry English is not my native language.
Slide with the rewards. So if you go back 2-3 slides.
Yeah, deep reinforcement learning we say the reward. Yeah, and the reward way does not show here. Yeah, but the training reward way does not show here because the training process we will show in our papers. Yeah.
What are the actions? I think that's probably related to the question.
Actions? Oh yeah, oh yeah. No, and the fish in this environment action is predation and refuge. Predation, the fish uses the physical vision, yeah, to get food from the environment, yeah. And yeah, and the flow, and the other action is refuge. Refuge is the fish use the physical vision to get in the refuge habitats and to avoid this hydro peaks. Thanks.
In your reward function, it looked like you had several parameters.
Yeah, yeah.
Choose those parameters. What is their impact on the result?
You say this parameter and firstly, we have refined the previous papers, reference the previous papers to satisfy parameters, and our involved simulation results should be consistency with the previous studies and papers to show a high consistency. Yeah.
So if I understood this right, you have some kind of energy cost. Would that be the hydrodynamic cost of generating those vortices? Is that the?
Could you be slow? sorry. Really sorry.
Energy cost.
Energy cost, yes.
Cost given by the hydrodynamic energy that's put into the vortices.
Yeah.
So that's your energy cost, and that has to be offset by some food energy, which depends on some kind of caloric value of the food bits that it takes up. Is it?
The energy cost most depends on the fish's tailbit frequency, and they use their muscle. Yeah, to use their muscle, and if they have high tailbit frequency, and they cost a high energy consumption, and if they use low tailbit frequency, and they have low energy consumption. Yeah.
Some other questions?
I was asking about the field of vision, so it looks like they look only forwards.
Yeah. Excuse me.
The field of vision.
The field of vision.
Where it looked like it is looking like a monkey.
Oh, vision, huh?
Yeah, not there.
Yeah.
You have a monkey fish.
But
It is looking forwards. That's very unusual for a fish.
Yeah.
Yeah, okay.
Okay. Thanks for your suggestion. Thanks.
So you use training, you use something called an actor critic.
Actor critic, yes. Soft actor critic, yeah. And what do you want to get from me?
What is
Okay. The actor critic. So the actor critic is the neural network architecture, and this soft actor critic is a reinforcement algorithms. So the agent do something, and this is the actor network. Yes. And the critical network evaluate the actor network's action and give them a feedback. So there are two networks such as actor network and the critical network, two networks, and they have different functions to learn and make some decisions. Yeah. Thank you.
Let's take the speaker again if there's no other.
Thanks.
Third talk. Enjoy the other talks or.
Thank you.
So you're staying here, but we have a break, 15 minutes, right? What's up? A bit more now. We don't even? Should have.